In this video, we'll learn how to evaluate the integral of 1 over the quantity a squared plus x squared times b squared plus x squared with respect to x using partial fraction decomposition. To use partial fraction decomposition, we express the integrand as a sum of simpler fractions. This will make it easier to integrate later. Let's start by decomposing the fraction. Step 1. Set up the form of the decomposition. Since our denominator factors into a squared plus x squared times b squared plus x squared, our partial fraction decomposition assumes the form. Step 2. We need to solve for a, b, c, and d. We do this by clearing the denominators. To eliminate the fractions, we'll multiply both sides by the common denominator, a squared plus x squared times b squared plus x squared. Let's expand the right side to find expressions for a, b, c, and d. We'll start by distributing both binomials. The expansion gives us, simplifying, we get. Now that the right side has been expanded, we'll use coefficient matching to solve for a, b, c, and d. Since there's no x cubed nor a linear x, those coefficients must each equal 0. Thus we have, and we'll also set the constant term equal to 1. So notice that the first two equations can be solved for a and c. From we can solve for a equals c and substitute into, which is, so we can factor out c to learn that. Thus, then from a is also 0. Next, we substitute these solutions into the third equation to find b and d. Since both a and c equal 0, equation 3 simplifies to. Solving for b and d gives us b divided by a squared plus d divided by b squared equals 1. To solve this equation, simply perform algebraic manipulations. Since we set and we substitute these solutions into the integral, and it simplifies to. This gives us a couple of simple integrals now. And now let's evaluate each integral. The standard result for integrals of the form is applying this result to our integrals we have. And that's how we evaluate the integral using partial fraction decomposition, by expressing the integrand as a sum of simpler fractions, solving for the coefficients, and then integrating each term independently. We simplify complex integrals into manageable pieces.